doing this. Take it away.
Thank you. Thank you very much, Vic. Very kind. Um, yes, I'm with Harris Miller Merlin Hanson HMMH. We're headquartered in Burlington, Massachusetts, but I myself work out of our Anaheim, California office. We're about 2 miles, well, maybe two to 5 miles north of Disneyland. So that'll give you some context of where our office is. And I'm presenting right now from Louisville, Kentucky. I happen to be on a project in Louisville, Kentucky today. So I'm on your time zone. So that's excellent. So yeah, about myself, I've been in this acoustical consulting world for my entire career. I graduated with a Bachelor's of Science with Aerospace Engineering from Cal Poly Pomona, here in California, there in California, and been working in this field ever since, doing various different things from modeling noise with military noise models and civilian noise models, working on sonic boom, working on uh, highway noise and construction noise projects and things like that in my past. So done a lot of things in the acoustical consulting realm, but aircraft has been uh, my favorite and my focus. Um, and so that's why when this project came along at HMMH, we thought this would be a great fit for us, and that's why we teamed up with Crown Consulting, which is they're the prime contractor on this project, and we are working under a small business, what they call Small Business Innovative Research project for NASA, developing this noise estimation framework for advanced air mobility. So this paper was to talk about the noise estimation framework of this, but there are some other pieces that I'll mention in the talk a little bit. And as Vic said, this was a talk I gave 2 months ago now at in Turin, and we were if and Vic, I'm sure you'll be empathetic, is we had a very strict time limit. We had 12 minutes, and then we had 3 minutes for question and answers.
Yeah,
So
they were really quite tough on the time limits,
yeah,
and the chairs were told to be tough on us, and you got it done. But hoping today we can be a little more leisurely
correct.
about it there, Joe. Thank you.
Correct. So I'll try to lengthen this out a little bit and give a little bit more in depth on some of these slides. And feel free to ask questions as we go as well. I hope that the Zoom will allow that. Okay, so let's go on to the second page 2 of the PDF, which would be the outline. And so this just shows an outline of my presentation, which follows the structure. We did write a paper for this conference, so this was just the presentation that accompanied the paper. And so this is basically the structure of the paper, the chapters of the paper, and so that worked well to be this also the outline for the presentation. So I'll give a brief background on the project, present our data and methodology, briefly discuss our results, conclusions and recommendations, and I'll close with acknowledgments. And like I said, I'll take your questions at any time as we go. The yeah, the acknowledgments are important because I didn't do this alone. So it's good. We'll acknowledge others and thank others for their help. All right, so let's go on to PDF page 3, which is the introduction background slide. The goal of the Advanced Air Mobility Community Integration Platform, which is just called the SIP tool. The SIP tool was to enable robust exploration of the potential for advanced air mobility design space, mainly safety, um, but also to look at evaluation of market trade-offs. That'd be the economics piece, and then characterization of other key challenges, one of which is noise. So noise is going to be potentially an issue with vehicles because of maybe not because of the single event noise that each of them makes, but on a cumulative basis and how many operations are going to be and whatnot. They may become annoying just due to their frequency of operations and the number of times they have to fly. Not just because they may be so quiet, but we'll see, right? The future will definitely be able to tell us. So the noise estimation framework is part of that overall tool set of looking at safety, economics, and then also noise was the other part of it. All right, so we'll go on to the next page, which is the continue with the introduction and background. Excellent. Um, community acceptance, then, if this is going to be part of the community integration platform, part of it is looking at how is the community going to accept all this, advanced air mobility and whatnot. And we think that it really hinges upon our understanding of two things, one of which is the vehicle's noise characteristics. You know, we got to know what sort of source noise levels we're talking about. And then secondly, we need to be able to predictly accurately predict, tongue twister there for me, accurately predict the noise on the ground from the source. So the source path receiver, you know, is your typical three things you got to do with noise modeling, right? So source characteristics, very important. The path and the prediction of the propagation of the noise to the ground, and then also then what do you do once you get it to the receiver? You know, how are you going to evaluate it? So so getting those noise characteristics is probably the most challenging piece of it because of the world we live in with, you know, it's proprietary data. A lot of companies don't want to give that up just yet. You know, the industry is so new. And so until only recently, and really only in a limited fashion, that competitive nature of the ARM market has caused manufacturers to not disclose or share such data. But NASA, Joby and NASA has worked together back in a year ago or so to do some noise measurements of Joby's vehicle. And so that's a start. That's great. This paper, however, because that data was not available when we were developing this work, we utilized source data given by NASA. So Steve Rizzi's group at NASA Langley provided the source data for two of their notional advanced air mobility vehicles. And for this paper, we compare it to existing helicopter data just so that you can show a little bit of context. They're not really, we didn't dive into modeling each vehicle like super accurately in terms of its performance characteristics. But we just wanted to, you know, if they all perform the same way, how could they, you know, what sort of noise exposure would they make? So we'll see some more of that.
One question.
Yes. Excuse me just for a second too. There's somebody knocking at my hotel door. Hold on a second.
Okay.
Oh, sorry about that. Yes, what's your question?
So an advanced air mobility device, we're talking like drones that would deliver packages to people. I'm assuming that's what you're getting at.
No, it's actually the larger type that can carry people.
Oh, okay.
Yeah, and maybe cargo, you know, maybe some small cargo or something also. So yeah. Yeah, not the package delivery drones, not the little guys, but the bigger passenger carrying type vehicles. So sort of like a Joby vehicle. Okay. All right, let's go on to the next slide now, the data methodology. All right, so we considered, we had to quickly choose a model that we're going to use for the prediction, and we thought about ADT. We had done some work with showing NASA a while back about the difficulties of modeling rotorcraft in ADT. You know, the helicopter modeling and whatnot that they have in ADT is really quite rough, and it's a little more difficult to get all the parameters that are needed for ADT. And so, although that's, you know, an FAA accepted model and whatnot, we thought that, and we looked at also SoundPlan, which is a commercially available product that you can also model. It's a simulation type model versus an integrating model like ADT. But SoundPlan has its disadvantages being a commercial product and whatnot, licensing and cost and whatnot. So we settled on the Advanced Acoustic Model, version 3.2, which we just refer to as ARM3, because a lot of people these days are now saying the word ARM for advanced air mobility. So, so we've had to make a allowance for that. So we call the computer model ARM3. And it's ARM3 is the part of the Department of Defense's noise map suite. It's distributed by the Volpe Transportation Center. It has roots in modeling of rotorcraft. In fact, its lineage dates back to the late 90s, where it started out as the rotorcraft noise model. And eventually they built it into, they changed it from not only being able to model rotorcraft, but also fixed wing aircraft. So, and then once it did that, then they started calling it the Advanced Acoustic Model. So it's sort of built for this type of application. So that was a definite advantage. It is a simulation model with two different modes to it. It can run in like a research mode where you can do just single events one at a time, and you can look at really detailed propagation stuff like wind gradients and temperature gradients if you want. And so that research mode has a lot of capabilities, and you can look at a lot of different metrics. And then it has also a multi-track mode where you can more like an airport type setting where you can have many flight tracks or multiples of flight tracks and not just look at single events. However, when you're in multi-track mode, you're limited. You have less metrics you can run and things like that, but it's got some capabilities for both. One of the great things about OM3 is that it accounts for variable ground elevation and ground impedance, whereas some other models don't do that. Like ADT doesn't worry about ground impedance. So it worries about the ground elevation, shielding, blockage, and things like that. Its algorithms, its sound propagation algorithms, have their roots in NASA's ANOP program, the Aircraft Noise Predictor Program. And so that's a powerful thing. It works off of its database is a set of 3D 1/3 octave band sound pressure level spheres, which is sort of depicted on the right-hand side of the slide. And it that allows you to full 3D directivity of the noise source, which is really important for rotorcraft since they throw their noise a lot differently than a fixed wing aircraft, say, does. So it's important to get that full 3D directivity, and the 3rd octave band stuff really helps with accuracy, especially when modeling terrain and other things where frequency dependency is important. And it can compute, as I mentioned, computes many noise metrics, including maybe things like audibility. You can also do things like making videos, visualization videos, and we're even trying to work towards the oralization piece of that too eventually. But it's a powerful model, and it was developed, like I said, it had its start back in the 90s, but it got a lot more development happened in the 2000s by Wiley and others that I worked with. So it's something else I was familiar with, right? More familiar with probably than AADT. So anyway, so we picked that one. So that's our data and our methodology. I'm going to get a little bit, well, at the start of our methodology, I'm going to then start talking about the data. Let's go to the next slide. All right, and so we are on, yes, make sure we're all synced up. So using their ANOP2, remember ANOP2 was NASA's program. NASA provided 1/3 octave band spheres. 1/3 octave bands went from 10 hertz to 10 kilohertz for two notional vehicles, the one shown on the left. One is the quad rotor, which is called the quad, and one is the lift plus cruise, L plus C. The quad rotor is has non-tilting nacelles. So it's just like a helicopter basically that has 4 rotors, and then the lift plus cruise has non-tilting rotors that are along the wing there, but it also has this propeller in the back, a pusher propeller, and that's where it gets a lot of its forward speed from. And the rotors are only active during vertical takeoff and landing. These spheres that the NASA provided are just for the rotor noise. They do not contain motor noise or the rotor airframe interaction or things like that. It was just the rotor components, but that's okay because I think that it's probably the propulsion noise source that dominates A-weighted sound exposure. So that was an okay assumption, I think. And then you could see some of the parameters of these vehicles in the table in the slide. Each of those 2 vehicles have gross weights around 6,000 pounds. Their airspeeds are similar in the 200 kilometers per hour. See, I'm talking in metric, but I was using also knots there in Italy. 100 some odd knots, right? 100 to 120 knots. And then the number of spheres that NASA provided were about 43 to 45 spheres for both of those vehicles. And there's our conventional helicopter shown on the right. This is a default vehicle that comes with the OM3. It's called the Griffin. It's a CH-146 Griffin. It's a Royal Canadian Air Force helicopter. It's 4-bladed. It's a utility tactical transport helicopter. has nearly the same, has 120 knot, 119 knot cruise speed, so it's close to the others. It's got twice the weight though, about 12,000 pounds, 45-foot span, but had also about 40 hemispheres. 41 hemispheres were in the database. So it's sort of a, just as a benchmark, just as a point of comparison. Like I said, we're not trying to draw any noise exposure comparisons, just the fact that we can run a helicopter in this model as well. If we wanted to look at, the comparison between existing advanced air mobility, which is really a helicopter, to future advanced air mobility, like some of these electric eVTOLs and whatnot. Okay, so that's the vehicles and the source data. Oh, so by the way, so these Griffin spheres are, like I said, default. They come with the model. So you get those spheres, when you get the model from Volpe. And there might be a couple other vehicles that are in that data set too, but the Griffin was mostly like a transport helicopter that you might see in these days. Okay, so let's go on to the next slide, which will be slide PDF page 7. Talking about the data now, so now that you've got the source data, you now have to tell the model how the aircraft flies and where it's going to fly. So where it's going to fly is the flight track. And so Crown Consulting, our partner on the project, they provide the trajectory, the flight track and whatnot, and the profile that you're seeing like on the screen. So the track was an origin at Cincinnati Northern Kentucky International Airport. It's called CVG, is the airport code. That's in Kentucky, to a small airport called Miami University Airport, OXD, in Oxford, Ohio. So it's a straight line track. We just decided to do something simple to start off with. Let's do a straight line track from one place to the other. It's a 30-mile route, and it's a 30-mile cargo type route. So it does have some realism. And the profile, so you can see altitude and airspeed on the graph on the slide. We took it up to 3,000 foot MSL. So it departed the vertiport at CVG, climbed right up to 3,000 feet, using up only about two minutes of flight time, then spends about 20 minutes of flight time in the cruise regime, where it stays about 3,000 feet, and then starts its descent and does almost a constant descent with a little bit of a wrinkle there at the back end at about the 20-minute mark. Airspeed, similarly, we had to give it some sort of increasing airspeed as it climbs, and so it goes up to roughly 100 knots as it's cruising, and then descends and slows down and whatnot, and steps down as it goes down in airspeed. I'm sorry, as it goes down in altitude. Okay. The quad rotor, it's got those four nacelles. OM3 allows a nacelle tilt angle to be input, and that's because you can tilt nacelles just like you can with the MV-22 if you're familiar with the Osprey that the Marines fly. It can tilt its nacelles from 0 to 90 degrees. So for the quad rotor, obviously, since they're fixed, they're non-tilting. We kept those at 90 degrees for all phases of flight. And the lift cross cruise nacelles were also 90 degrees, but we changed that to 0 degrees in cruise because we knew that pusher propeller was working. So we used 0 degrees in cruise. And then, of course, you have to model the terrain that's in between those locations. So we used the 30-meter national elevation data set from USGS to model the terrain. And for impedance, we use the national land cover data from the web, and that was very helpful. Weather conditions, we can plug any weather conditions we want in terms of temperature and humidity, but we just chose standard day for this one, which, as you may know, is 59 degrees, 70% relative humidity. No wind or temperature gradients were modeled. In this particular one, we did run it in research mode in this case. So, but we didn't decide to. Again, we wanted to keep it simple to start off with. So this is our first case. All right, let's go on to the next slide. Yes, sir.
When you modeled the lift plus cruise at 0 degrees, you were saying for the rotors. So is that the equivalent of you turning off the lift rotors and then only using the propulsion motor? Or
yeah, because I'm assuming that the source data, the spheres for those when it was in cruise, was just the push propeller. I figured that the lifting rotors must have been off when
Okay.
they created that vehicle. Yeah.
Okay. Very good.
The wings providing a lot of the lift at that point when they're in cruise flight too, forward flight. All right, we can go on to the next slide. Metrics. We computed sound exposure level, A-weighted maximum sound level, and day-night average sound level. And the DNL was built off of the SELs using the equation shown there on the slide. Simple equation that just relates, SEL plus 10 log of the number of events minus the time constant, which is 49.4 dB. So that's just, taking the number of seconds in a day is subtracting off. That's 49.4. So you're just normalizing SEL to a whole day, and you're adding the 10 log of the number of events. That's what any of the models do, ADT or noise map or any of those. So, and it makes it simple because then you could just run single event contours and then tell the number of events you want to run and what time of day they're in. Most of them for this study, it was all daytime events. So you could just plug those in and then morph that grid. That's what's good about this with the SIP tool is that if somebody, we could pre-process a lot of these sound exposure level contours, and then the user can say, well, I want to try 1,000 ops of that. No, I want to try 300 ops of that. And I want to put 10% at night and stuff like that. And you can play around with those types of gains to see how that affects your noise exposure on the ground. One of the hard parts was creating the rectangular grids. For such a flight regime, we had to create a large rectangular grid for that fairly vertical flight track you saw, north-south running flight track, going from CVG to OXD. And but you could definitely understand that if you have a track that does a lot of turning and traversing a lot of country, that your noise grid could be huge for that. So you may have to break it up and do smaller grids and then patch them together in post-processing. And that sort of spoke to our basic tasks list or processing procedure, which is shown on the right. We had a preparation sort of module, and the duties there were to define the study area, collect and prepare the ground elevation impedance data. Then there's the computing part where we're actually getting that input trajectory from Crown. We're generating an input file for OM3 and then running OM3, post-processing, looking at the outputs, and then calculating these cumulative metrics like DNL, and generating noise contours as in shape files, GIS shape files, to then give back to Crown, and they can then finish with the rest of the tool. So our part was, give us the trajectory, we'll compute the noise for you, and we'll give the noise back to you in a shape file. Then you can have the rest of the SIP tool do possibly population impacts and any comparisons of scenarios that the user may want to run. All right, so let's go on to the next slide. So the results, what we showed in the paper was this 3 blocks of images that you're seeing here on this screen, but all together in one vertical thing, so you can sort of easily compare. But when you when you take your presentation and you make it landscape, you have to make room. So I've got it in 3 separate pieces. So up top, you're seeing the arrival portion. Let me start at the bottom. At the bottom right, you're seeing the departure portion of the flights. In the middle of the slide, you're seeing the entire trajectory, but mostly the cruise portion is what you can make out. And then we zoomed in for the top left. We just zoomed in on the arrival portion of the flights. And you're seeing 3 slides in each one. One's the quadcopters on the left, lift plus cruise is in the middle, and the CH-146 is always on the right in each triplicate, in each triple of images. And so again, we flew the CH-146 just like the lift plus cruise and the quad rotor, same profile, same power settings and things like that. Just of course the spheres are so the same speeds, altitudes. There's no power settings, so just speeds and altitudes ran in the same flight track. And you can see that it produces a noise contour throughout the whole trajectory if it's real, but whereas the quad copter and the lift plus cruise really for this was number 3. This was 300 daytime operations. So that's, if you look at it, that's 20 ops per daytime hour. and they didn't produce hardly anything. They produced a little bit of a contour up at the vertiports, at the arrival vertiport and the departure vertiport. So, and these contours were based on a 500-foot noise grid spacing, like I talked about. So we created a rectangular noise grid that had 500-foot spacing for the entire trajectory. And that run took about 90 minutes for each vehicle, 90 minutes for each vehicle per trajectory. And that's on a typical laptop PC. So the SIP tool, like I said, will eventually compute the population exposed to each 5 dB band. Here we ran 45 to 90 in DNL. And so they'll compute the population underneath that. So they'll use census data to do that. And like I said, they'll use that to compare and contrast different trajectories and different vehicles and scenarios. And so this is just a notional example of such a comparison. Okay. And then the last slide, let's go to the next slide, page 10. Conclusions and recommendations. So we conclude that the framework, we have built this noise estimation framework for the SIP. It allows estimation of noise exposure from advanced air mobility type operations. It leverages the Advanced Acoustics Model for its accurate calculations. Recommendations that we've already sort of worked through since I wrote the paper back in May, was that we are computing CNEL. So DNL is used for 49 states in the U.S. CNL is used for California. That's the community noise equivalent level. And so it allows the computation of that. The only difference being really is the CNEL, if you know, has an evening component. So it has a weighting and an evening component for operations. So it's not that hard to implement. And then obviously we want to model local or regional weather conditions. So we'd have to get weather data sources like from NOAA or something off the web, where you can get, what's the typical or average weather in the region that you're trying to study. But we think that that's, we can't be running standard day all the time. So that's why we want to use, local conditions. And, the 90-minute runtime is not great. So we might want to look at reducing those runtimes. That we might do that through segmenting these grids a little bit more. Maybe for the cruise portion is run at a more coarse grid spacing so that the model runs faster for the cruise portion. And maybe the more tighter spacing, like 500 feet for the near vertiport phase of the analysis. So might want to do that to help speed things up. It might require a little more processing where you have to patch those grids together at the end, but at least the runtimes would be, I think the runtimes would be greatly reduced. And I thought I had some numbers on that at my fingertips, but I don't. So I'm going to say that I think we've done that work already and looked at the time savings, but I think it was significant. I just don't have the numbers off the top of my head. Okay, and so acknowledgements, next slide. So a lot of this was worked on and written by one of my colleagues at HMH, Mihir Rimja, Tim Middleton, and then we've teamed with the University of Cincinnati, Dan Cupoletti, and also Peter Sorensen, one of his students. And then we had Paul Cobb at Crown Consulting, was the project manager, like I said, for the prime contractor. They're based in Arlington, Virginia. And as I mentioned at the top, it was through a NASA SBIR, Small Business Innovative Research Program, that we got this funding. And I'd like to thank Steve Rizzi at NASA Langley for providing those spheres for us. That really helped speed up the project and gave us a good foothold to start with. And so with that, I said grazie in Italian, grazie. And so I asked for questions in English at the time, and I'll still ask for questions in English here. So if you have any more, I'll be happy to take them. Thank you.
Okay, so thank you all. I'm actually going to stop sharing just briefly so we can sort of see each other. Thank you all. And thank you, Joe, for presenting. I think we're going to have a number of questions for folks. And so instead of everyone over talking each other, this time we'll use the reactions thing down below on the Zoom to see who wants to, in fact, raise hands or whatever. So if you have a question, go ahead and raise your hand. And Siddharth, how are you today? And you want to unmute yourself and ask your question.
Hey, Sid. Your audio is not coming.
Perhaps your audio is not coming through, Siddhartha.
Cannot hear you, Sid. Sid is.
So we can't hear you. I see in the chat.
Yeah, he says, please go to someone else.
Chance while he works it out. Okay, so so who would like to ask a question then? Goran, sir, how are you?
Fine, thank you. And thank you, Joseph, for your interesting speech. One question which comes to mind is, how do you get the information about the noise of the source, the first hand, in order to able to inject it inside? Because it has to be given in free from the surrounding effects, because you are adding the effect of ground later in the program, if I understood well. So it must not be very easy to get this information in the first place. You said in your speech that you had that it is not easy, that some companies are willing to produce that.
Correct.
But
Yes.
if they are not, and if one does have a source, really, how to extract the intrinsic part of the noise, which comes from the source only, without the influence of the surrounding in which the noise is measured, like reflections from the buildings, if the source is at the ground, or if it is in the air.
Yeah, of course. Right. You want to measure it, and you want to measure it, of course, free of reflections if you can. So you want to measure it in a big open area usually, and you can take this data from, if especially for level flight, you have it fly across a microphone array, and then take that data and acoustically repropagate it back to the source. So you can take a ground array of microphones and repropagate that as you have the aircraft fly over the array. Hovers and whatnot are same way, except your microphone array is just probably shaped differently. It might be shaped in a more of a circular type of arc, to get that sort of directivity. But you have to repropagate it. You have to measure it. You have to measure it free of a place of reflections and stuff. When we measured reference vehicles in the past, like for fixed wing aircraft, we've done it in the desert. We've done it up at Edwards Air Force Base or something like that, where the ground, we know the ground is uniform, and it's fairly hard and reflective. But use ground plane mics and stuff like that. You got to use the proper processing techniques and measurement techniques to get the data so it doesn't have reflections in it. But it is possible, and it is doable. So if you have the vehicle, you just got to measure it. You got to measure it and then create the spheres for it.
Okay, very good. Thank you.
Thank you.
Do we want to come back to you, Siddhartha?
Yeah, can you hear me now?
Yes, we
All right,
can.
great.
Welcome.
Hey.
Okay, great. Thanks. So I have, I think well, one question is on the helicopter. You said it's a 4-bladed rotor, but it also has a 2-bladed tail rotor.
True.
Was the tail rotor information included in the source
Yes.
noise?
Yes. Yes,
Okay.
it was. Yes.
Okay. I was actually surprised. And you referred to the quad rotor as the quadcopter, just to let you know it's the quad rotor. Yeah, I get confused. I mean, I got confused when I first started working with it. And it's the quad rotor. Quadcopter is the drone.
Okay.
But the I was actually surprised at how lower it was, because that quad rotor. I mean, I've oralized the sound and listened to it. It's not that quiet. So it was pretty interesting to see that result. And also, you said this was SBIR. Who was the NASA TPOC on it?
Her last name is escaping me, but her first name is Nancy.
Nancy Mendoza.
Yes, ma'am. Yes, Nancy Mendoza.
Okay. All right. Thank you.
Right.
And this was a phase
Question.
one. Sorry.
This was phase, I think it was phase one. No, it's phase two. Phase one was sort
Phase
of
two.
it was
Wow.
phase two. Conceptual was the phase one, I think, where it was just sort of, what are we going to do? And then phase two is actually put something together. And so that's the phase we're in now. And we're at near the end of that. I think we have another 6 months or 8 months to that
Okay,
phase.
thanks.
Okay. Gordon, did you have a second question or
Yeah, I do have one.
okay,
if
go
you
ahead.
allow.
Yeah, go ahead.
Yes. It is to be expected that the flying vehicles like helicopters and similar vehicles will invade cities in future, especially due to the shift from fossil fuels to electric drives. And the question is then, do you think that it would be possible to upgrade the program, such as your AM3, to the scenarios where you don't have a plain ground defined by its elevation and impedance below the vehicle, but also you have a city with its buildings, etc., which substantially would change the conditions of reflection and absorption of noise?
Yeah, yeah, currently, it's a great question. Currently, OM3 does not have a capability for modeling barriers, like thin screen barriers. I'm hoping that it'll be, I think it's on the drawing board. I think it's on development, but it's not in there yet. But it's one of the things we've wanted to have in that program for a long time. And once that gets put in there, then it'll be able to better model buildings. And the reflection is definitely an issue. With urban canyons and things like that, I think that is an issue that we want to work out as well. So far, I'd say the answer to your question is maybe that it might be able to do that in the future. Currently, it cannot. That was one of the advantages of SoundPlan, was that SoundPlan has got that capability already in it. People model buildings and stuff like that, night and day with that thing. So it's already got that built in. So that was one of the, wish I could have had that capability too in OM3, but not quite yet.
Okay, well, thank you for that. Greatly appreciated. Any other questions people would like to ask at this time? All right. Well, hearing none, again, Joe, we very much want to appreciate your spending time with us today to do this. Now, I've done this several times and it's been successful. So I want everybody to turn on their microphones. Yes, turn on your microphones. And let's give Joe a round of applause. Thank you all very much.
It does work. Thank you. Yes, appreciate that.
It does.
Thank you very much.
Yeah, very much so. And thanks for doing that. And again, we're going to wrap up this seminar today. I hope everyone has a great rest of your day, great weekend, and look for us having another seminar of this kind in the spring sometime. And if you have any questions or comments, please go ahead and forward them to me, and then I'll be happy to send them to Joe or anybody else. So again, thanks everybody for your time, and have a wonderful day.
Thank you all. Thank you very much, Vic.
It was a pleasure, Joe.
Yes, good to see you again. Bye now.